this is how you negate it. That's super easy, right? But how do we apply De Morgan's law to it? We move the line and we flip the sign. So hopefully you guys can read that over here. This one's clean and a couple of them are still clean on the board so you can see it. But so the first one is saying, the original one, the very first thing we started with is saying, for all x, whatever the domain of x is, we don't know, but for all x, x squared is greater than x, okay? If the domain is vegetables, then it's probably not true. But assuming it's numbers, this is probably okay, right? All right, unless we're squaring 0, then it's a problem. But we're claiming that it's true for whatever the domain is. The next line, the first green one on the screen there, we're saying it is not the case that everything in the domain when squared will be greater than x. In other words, there exists some x in the domain such that when you square it, it will not be greater than x. That's what happened when we applied De Morgan's law. All of those are the same thing. Yep. Okay, next up. This is how you negate it. Again, you simply just put the negation symbol to the left of it or on top of it, right? And our original claim, the first claim here, is we're saying there exists some x such that when you square it, it will equal 2. We're saying that exists. Okay? The next line, we're negating that. And we're saying there does not exist some number such that if you square it, it will equal to 2. Right? We applied De Morgan's law, and we see we moved the line and we flipped the sign, right? The line went here and the sign flipped to that. So we're saying that for all x, there does not exist one that none of them, if you square them, will equal 2. Okay? Make sense? So first up, let's apply De Morgan's law. A good rule of thumb when you're doing a proof, look around and see if there's a place to apply De Morgan's law, and oftentimes you will find that will lead you down a path. The whole goal of this proof here, and then again, this is very informal because I haven't shown you the full official way to do a proof, but the whole goal is this. I'm trying to mathematically manipulate that so that it looks like that. That's all I'm trying to do. That's all a proof is. You're making some claims over here and you're trying to mathematically manipulate the claims to look like the other thing that you're claiming they will eventually can look like. Okay, that's all that's going on here. So right off the bat, why would I want to apply De Morgan's law if I'm trying to make this look like this? Because De Morgan's law will flip the sign, because I know I need one of these, right? Right now I've got this guy. Well, if I apply De Morgan's law, this becomes that, and so now I'm sort of on the right track here. I got an existential operator, which is what part of what I'm looking for. So the next thing is, I have my existential now. Basically, if I can just make this become this, or vice versa, I should say, then we're done, right? Well, it just so happens there's a nice little fun rule right here in this table, and it is this one right here. Okay? This guy right here. So first thing I did was we applied De Morgan's law, and we moved the line, flipped the sign, okay? We end up with this. But now look what we have inside of here. We just simply have a P, therefore Q that's been negated. Do you agree with that? Okay? Think of this P and Q business. You might have a whole slew of this and this and this. Therefore, R of X, whatever. That's still a P, therefore Q. All right, so if we understand this idea that this is simply a P, therefore Q, well, you can see that this rule right here in your table number 7, that a negated P, therefore Q can become a P and not Q. You see that? This means yes? Yeah? Okay, good. All right, so then by applying that rule, this right here becomes that. Agreed? Okay. So if that is that, if I plug this back into here, I now have existential operator P of X, I should say quantifier, not operator, and not Q of X. That is that. all I did along the way is just rearrange this algebraically or mathematically or logical equivalency ways, right? That's a word, I made it up, okay? But eventually we arrived at manipulating this to look like this, okay? Now, when we get into proofs a little bit more in depth, you're going to find that sometimes you're going to try manipulating and it's not getting there. Like, what's going on? Let's try a different approach. But I want to pick an easy one to start with, okay? Good? To the whiteboards. So let's look at the first one here. This first sentence says, express the statement, every student in this class has studied calculus, do that using predicates and quantifiers. Next one, some student in this class has visited Mexico. Again, express that using quantifiers and predicates. And the last one, express the statement, every student in this class has visited either Canada or Mexico. Okay? Start with the first one. What kind of things do we need to consider here? And that should be translating English to math, by the way. So we're looking at variables that we need. What else? There's a big question that we need to answer before we can do anything. What's the domain? We're the ones that wrote the sentence, so we can decide what the domain is. Okay? So depending on the domain you choose will determine the equation you end up with. And that's the point I wanted to show you here. So if the domain is all students in this class, so it's just us 15 or 20 people here, then we can have a function here that's called student C has studied calculus, and we can simply say for all x, C of x. And that translates that sentence into math. Okay? Sorry about having this backwards here. Not sure why I did that. But what if we chose a different domain? What if I chose a domain of all people? And I had a function that's called S of x, which is person X is a student in this class. And we'll keep this function here. Now I can say this. For all x in the domain of, for all people, for everybody on the planet, if that person is a student, therefore they have taken calculus or studied calculus. See how the domain changes things? Okay? How about this one? We can make a function here called q of xy, which is student x is studied subject y, using all students, and all students in this class, I should say, okay? So in this class, I just didn't write that out, I meant to. Then I can say, for all students in this class, that student has taken calculus. Another way to write it. Okay? What questions do we have on this idea here? We good? Okay, last one. Let's look at the same premise above here, or the same predicate here, domain of all people. We could have, and again using this S of x here, for all people, if you're a student, therefore, that a student of this class, therefore, that student has taken calculus. Okay? So domain changes things, all right? Questions on that one? The big message that I hope you guys took from this is that domain matters. Depending on the domain will determine what your final result will look like. So let's start off with this domain, students in the class. If the domain is students in the class, and then I think you guys can surmise that m of x means x has visited Mexico. I think that's pretty clear. Again, in a real proof, you'd have to write that out, but I'm just for time's sake here, right? So in this case, yeah, that's easy. And a lot of you got that one. You didn't use M, use P or whatever, that's fine. Okay? How about a domain where it's all students? Just all students on planet Earth or in the universe or whatever. So now we have a function called S of x, and let S of x be the statement that x, so that should be an x there, x is a student in this class. Okay? M of x is still a student that has visited Mexico. So the next thing we're saying now is there exists some student in the domain of all students such that that student is a student of this class and they visited Mexico. which is, again, some students visited Mexico, right? And I pointed out to you, I think I did this off camera, so it's not recorded, so I'll mention it now. You could argue that you should be using the existential here because I'm saying some student. All right, a better wording with that would be at least one student. All right, so I wanted to go with the not the uniqueness, but the existential, right? I keep calling the uniqueness an existential. I don't mean to. So don't use this one, use this one, right? Okay. All right. Next up, let's try another domain. What's happening here? Well, it looks like I just gave you all the answers to the next one, unfortunately. I don't have a slide that hides that from you, so let's just talk about it. Sorry about that, guys. That's really bizarre. I thought usually what I do is I'll copy the slide in, then I'll make like 5 or 6 versions of it, and I'll delete one line for each one. I must have just forgot to do that here. Sorry. So this is a different statement, though. All right, this is one I was going to have you do on the board, but we'll just do it here. Every student in this class has visited either Canada or Mexico. Okay? Well, if we're going with the domain being, well, let me ask you, what is the domain of that first one? Students in this class, right? Students in this class. Okay, so this is, I don't know if my next slide is going to show it, but we'll just say students in here. Okay, what's the next one down here? It could be, yeah, I haven't defined what those functions are, so it's hard to tell, but it could be all people, all creatures, it could be all anything, as long as my S of X means something like is a student in this class. So my claim is for all things in the domain, whatever that domain is, it's every object on the planet, let's say, so cars, trucks, people, dogs, cats, whatever. If that object is a student of this class, therefore, they have been to Canada or been to Mexico. Okay? What do you suppose the last one is? The domain, let's talk about the domain first of the last one. What's the domain? Yeah, it's pretty much the same idea as this one, but what's going on here? Aaron. Yeah, I made a function with 2 variables, right? So I have v for visited, and we have x and y, which means this would be let v of x, y be the statement that x has visited y. Okay? So I just plugged in x, which is the x in the domain that we're talking about here, and I plugged in the actual place that we know they visited. So they visited Mexico or Canada. All right, take a look at this. The next thing we're looking at here is nested quantifiers, right? This is, we got some 2 and 3 levels deep nested quantifiers. So we'll look at these quickly, and they should make sense pretty quickly. But look at this statement here. What do you suppose we're trying to say there? How would you pronounce that? Forget about the making it super English friendly. Just how would you pronounce that mathematically? For all x in the domain of x, there exists some y in the domain of y, such that all the x's plus that y will equal 0. Okay, that's what that's claiming. Right? Whether that's true or not, hard to know. We'll talk about that in a minute. What about this one, the second one here? What are we saying there? Yeah, do the thing. I like it. Yes. Do the thing. Right? That thing you do. So for all x's in the domain and all y's in the domain, if you add that each x individually to that y that you're looking at the moment, it will be the same thing as y plus x. I think that's obviously true, right? Duh. Okay. All right. Let's look at this one. For all x in the domain of x and all y in the domain of y and all z in the domain of z, that each, again, we're looking at this individually. Think of this like a loop, okay? We're looking at this like a loop. These are like for loops. This is like nested for loops, okay? That's exactly what's going on here. So we start off with our outer loop, which is going for x, ... to whatever. And inside of the for x loop, we have Don't know what just happened there. Why you do this to me? Weird. Inside of the for x loop, we have a for y loop. And inside of there, you have a for z loop. So when x is equal, let's just say we're going from 1 to 10. When x is equal to 1, why? Why? When x is equal to 1, we get to y. Y becomes 1. Then, what the heck is happening here? Weird. Y is equal to 1. Then when we get to z, it's equal to 1. But z is going to loop however many times it's supposed to loop, right? 10 times or whatever. Each time z is looping from 1 to 10, y is still only 1. X is still only 1. You see that? Okay? And then once z is done iterating 10 times, then y will increment, and we'll go through the whole thing again. Okay? So think of it that way. If we're looping through this kind of thing, we're saying that for all x, all y, all z, that x that we're currently looking at the moment with the y plus z is equal to that same thing. For every combination of x, y, or z, this will be true, is what we're saying. Okay? And I think that's clearly true, right? Last one. This time I'm going to tell you the domain is all real numbers, and we're saying for all x in all real numbers and all real numbers y, if x is greater than 0 and y is less than 0. In other words, I have a positive and a negative number, right? X being less than 0, y being greater than. If I have one less than, one greater than, therefore, if I multiply them together, the result will be net less than 0. Right? So all of these are true. Let's talk about the first one. I think the other three were pretty intuitive, right? How do we feel about that first one being true? For what this is saying, for every single value of x, let's just take a short domain here. 1, 2, 3, 4. Okay? Let's not worry about the domain of y for a moment. But right now, x's domain is 1, 2, 3, and 4. For every value, so for the value 1, for the value 2, for the value 3, and the value 4, there is some number in the domain of y that if I add it to the value I'm looking at, it will become 0. Right? So if my domain of y is -1, -2, -3, -4, we could see that for every x, there is a matching y that if I added it to it, it would give me 0. Okay? Now, it's hard to tell that truth value without me specifying a domain. I should have told you ahead of time that the domain is real numbers. Okay? Because that's negative and positive, and that would make that true. Right? How do we feel about all that? Good? Okay. No question? Yeah. His question was, does the order matter? And the answer is, order matters sometimes. Okay? All right. So, it's funny that you just write it like it's like you timed it perfectly. So let's take a look at this statement here. Let P of x be the statement x plus y equals y plus x. Okay? That's probably true. What's the truth value of this? Assuming, let's go with all real numbers. True. Now notice the next one, I just rearranged the location of the variables right here. What's the truth value of that? Also true. Okay? Those are both true. So when you have nested same type quantifiers, so if I had all universals or all existentials, then the order does not matter. Okay? It doesn't matter. If you're mixing existentials and universals, then order can matter. In some cases it does, some cases it doesn't. Okay? So let's take a look at this. This is our statement. Q of xy is equal to this. What's the truth value of that? There exists some y such that for every x, that x plus y will equal 0. For a whole, let's go with the integers, yeah. That is false, okay? Because that would mean that every single number, no matter what it is, there's one number, if you add it to that number, it will always equal 0. Like there's some magical number out there that if I add it to 5, the result is 0. But if I also add it to 7, the number result is 0, right? No such thing. What about the next one, though? Yeah, for every x, there exists some value y such that when I add it to the x, it will be equal to 0. Yeah, there is some value out there, just not some value that works for all numbers. But all numbers can find one specific value. So in this case, the order makes a difference. Those are the same equations, but the existential and the universal are in different orders. That changes the meaning. So what is the truth value of this? We have a function with three variables in it, and I'm claiming that for all x and for all y, there exists some z such that if I add the x and I add the y, it will equal some value z. Yeah, I'm just basically saying that there's, again, assuming the domain is all real numbers, right? Let's go with, that's the symbol for real numbers. The domain is all real numbers, then I'm basically just saying that any two numbers I add together, there's some other number that they will equal, right? That's all I'm saying. Okay, this one, there exists some number such that all x's and all y's when added together will equal that number. That's that magic number again, right? Like that magic number is 7. No matter what I add, everything x plus y is always equal to 7. That's ridiculous, of course, right? That's not the case. So that makes this thing false, as we saw on the next slide there, okay? The next thing we're going to look at, which will not be today, it will be next time we meet in a week, we'll look at negating quantifiers that are deep like this, applying De Morgan's law to it, and we got a whole bunch of problems that I want you guys to work through in your teams to figure these out, because as you pointed out, Amanda, the only way to get good at this is practice, 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 right? So any questions?